Good day and welcome once again to our class on real analysis. In today's class, we'll be proving the convergence theorem on subsequence. This theorem is similar to the sequential limit theorem, but the sequential limit theorem is a two-directional theorem, while the convergence theorem on subsequence is just one direction. And the theorem states, if x of n is a convergent sequence, then every subsequence of x of n is also convergent, and the limit as n tends to infinity of x of n is equal to the limit as I tends to infinity of x of ni. An alternative way of stating this theorem is to state that if x of n converges to x, then every subsequence of x of n also converges to x. Now, to prove the theorem, let x of n be a sequence with terms x1, x2, x3 down to xn, and it continues like that. And let x of ni be a subsequence of x of n with terms, what will be the terms? That will be x of n1, x of n2, x of n3 down to x of ni, and it continues like that. If xn is an increasing sequence, if xn is an increasing sequence, then it means that what? x1 is less than x2 is less than x3, and that is less than xn, and it continues like that. Assume xn converges to x. Assuming xn converges to x, then by definition of convergence, it implies that for any epsilon greater than 0, there exists a k belonging to the set of natural numbers such that the absolute value of Sn minus x will be less than epsilon for all n greater than or equal to k. Now, what do we want to show? Before that, this also implies that the limit as n tends to infinity of x of n is equal to x. We want to prove that for any epsilon greater than 0, there exists a k belonging to the set of natural number such that the absolute value of x of ni minus x will be less than epsilon for all I greater than or equal to k. Since we said we want to prove that every subsequence of x of ni is convergent, and that means that we want to show that the limit as I tends to infinity of x of ni is equal to x. But recall that x of ni is a subsequence of x of n. X of ni is a subsequence of x of n. Therefore, it implies that x of n1 is greater than or equal to x of 1, and x of n2 is greater than or equal to x of 2, x of n3 is greater than or equal to x of 3, and that moves down to x of ni, which is greater than or equal to x of I, and that moves to what? X of n. Therefore, we can imply that I is less than ni and ni is less than n. Let epsilon be greater than 0 and I be greater than or equal to k. It implies that k is less than or equal to I, and if k is less than or equal to I, then k is less than or equal to I, and I is less than or equal to ni, and that is less than or equal to n. If we reverse that, we have n with greater than or equal to ni, greater than or equal to I, greater than or equal to k. By definition of convergence, we have said that for all n greater than or equals to k, we have what? We have the absolute value of x of n minus x to be less than epsilon. Therefore, since I is greater than or equal to k, then the absolute value of x of ni minus x will also be less than epsilon for all I greater than or equal to k. This implies that x of ni converges to x, which implies that the limit as I tends to infinity of x of ni is equal to x. But remember that since x of n converges to x, the limit of x of n is also equal to x. Therefore, this also further implies that the limit of I tends to infinity of x of ni, which is equal to x, is equal to the limit as n tends to infinity of x of n. Therefore, the limits are the same. Limit as I tends to infinity of x of ni is equal to the limit as n tends to infinity of x of n. Therefore, if x of n is a convergent sequence, then every subsequence of x of n is also convergent, and that is the proof for the convergence theorem on subsequence. If you have gained anything from this video, give it a thumbs up like, share with your friends and colleagues. Thank you for watching thus far. Have a beautiful day and God bless you. I see you in the next video.